topic is innovations in water quality management and global water sustainability. I have swapped it because it would be more logical to start with global water sustainability, and then I will show you some innovations in water quality management. Some innovations, some solutions, and also some challenges what we have, which we have not solved yet, but I believe that we have to do it in the coming years. So I'll start with some basic stuff, which I'm sure that you know about this, but it will probably refresh your mind and it will put everything in the context. So we hear about the water scarcity, but when we go anywhere, we'll see seas, rivers, and lakes. So it's almost everywhere, right? So then it raises a question: is there a scarcity, especially for you and I, who lives in Canada and Norway? We don't see any scarcity, but in great parts of the world, we experience this. Examples like this. These are probably lakes or rivers and completely dried off. And if you Google about water scarcity, you will see some quite a few of interesting scenarios and history, like the Central Asia. And before it was an issue for Sub-Saharan Africa, water scarcity, but now we know that in the US, Australia, in EU, everywhere the water scarcity is coming up. So this is also a fact that I'm sure that all of you know about. So in fact, 70% of the world's surface is covered with water. Yet we talk about water scarcity because less than 1% of that water is accessible to us, because a great part of the 70% are in seas, which are saline, and another big part is in groundwater aquifers, which are deep down, which is not feasible for today to take up, and the other part is in icebergs, which is also not so feasible. So that's why we talk about that we have very little amount of water is available. And then there are figures produced by think tanks using some models and also some other approximations saying that how it is going to be in the water stress or water scarcity. So this figure shows the difference between the water demand to the available water. And here you can see that all the dark areas, those are the places are going to see critical water stress by 2050, but some of them already have it. And then all the red parts and even the yellowish parts are going to experience this water scarcity. So what was the challenge? The challenge is that in year 2000 we had little over 6 billion people, and by 2050 we are going to have 9 or 10 billion people, a 50% increase of the population. So we had 200,000 cubic kilometers of fresh water back in 2000. It's going to be more or less the same in 2050. So 50% increase of population, but amount of water is the same. And the other problem is that water which we talk about, it is unevenly distributed among the lands. Like Canada and Norway, we have abundant amount of water, which we really don't need. But if it is distributed evenly, probably it's going to be enough, right? The other issue is that climate change will make things worse. But not only that, we are not using our water resources properly. We are actually misusing them. So this is an updated figure from 2020. It shows the amount of wastewater which is discharged to the environment after a reasonable treatment. A reasonable treatment does not mean that it removes phosphates down to 0.5 or 0.3 milligram per liter, and nitrates down to 6 or 8 milligram per liter, or COD below 100. It's not that, it's far from that, but it is a fairly acceptable levels, and you can see that the world's 44% of wastewater in the world is discharged to our water sources, water courses. A part, of course, go to the sea, the other part goes to our freshwater resources. So it means that the little amount of what we have, they are also becoming inaccessible because of this unsustainable use of our water. Then the last few years we start to talk about the reuse of water. This is also, I understand that Professor Bra's team is also working on the water resource reuse, because until about maybe 2 decades or 3 decades, wastewater treatment was considered as a cost only, a headache. Nobody wanted to work on this because this is just a cost, right? But things are now changing. So here it's a figure illustrating how we can increase the water reuse. We take the water from raw water sources and we purify them, and then we supply to industries, municipal use, and agriculture. So the old way of working on this is that we just send them to treatment and then to discharge that, or sometimes even without treating. So it's now changed. So we are trying to reuse as much as water which we collect back to the industry, back to the municipal and other agricultural users, and then we are going to recover something, recover wastewater and use it here, or treat them and send back to our water resources. So in that way, although our use of water is increasing, but still the demand could be a little bit under control. One of my colleagues, Frank Rogola from COFIN, he showed this figure maybe 20-25 years ago. He said, we will not talk about wastewater treatment plants in the future, we'll talk about energy factories. So in fact, it's what's happening. There are, although there are few, there are a number of treatment plants in the wastewater treatment plants in the world which produce an excess of energy. They are self-sufficient with energy, but not only that, they also supply energy to the national grid. So I think this is we are going to see more and more in the coming times. And another issue is phosphates. If you don't have phosphates, the agricultural production will suffer in a serious way. So it says that by 2033, the mineral phosphates availability starts to go down, which means that we have to find a way to recover phosphates. So already in a number of countries, this has become a legal requirement. If you take Germany, Germany has prohibited sludge treatment, all the sludge treatment methods other than incineration, because of the space issues and other disposable issues. But it says that before incineration, you have to recover phosphates. And I think the main or most popular, most common way to manage sludge, wastewater sludge, is now to generate biogas, but still it's not happening everywhere. And in Norway, we have been using our sludge in agricultural lands because heavy metal content is extremely low in Norwegian wastewater. Because that we have been disciplined to not to throw everything into our wastewater systems. Right? So Norway is one of the few countries which legally allows to use wastewater sludge in agricultural lands. So up to 8% of our sludge was used in agricultural lands, but it's now reducing because we are also starting to generate bioenergy or biogas from wastewater. So we have estimated 20% of the phosphate needs for agriculture, it is in our wastewater. So we think at least 10% of that, at least half of that, we could be recovered, which means that the additional phosphates we need to bring into our agriculture should go down. Right? But in many places we are also not doing that. But there are now new, not new, but old concepts, but there are new applications like generate struvite from wastewater and wastewater sludge. Struvite is ammonium, magnesium, no, calcium, ammonium, magnesium phosphates, right? This white crystal-like things. Or in wastewater we have enough ammonium, enough phosphates, but we don't have magnesium or potassium, so sometimes we add that, then we can get the struvite out. So to continue with the issues pressing our sustainability of related to water, there are these factors I would like to mention: the urbanization, lack of land. You might wonder why, what has that to do with water, and virtual water, and climate change. So urbanization, these are some statistics and also prognosis of the urbanization in the world is this blue line, and then the regions. Africa is red, Asia is green, Europe is there, Northern America is also up there, and Oceania also there. So what you can see is that all these countries, the Northern Europe, Europe and Oceania, so the increase of urbanization from 2025 to 2050 is maybe between 7-8% to 10%. But if you take the situation in Asia, Africa, and Latin America, 2025 is here, and 2050 is here. We are talking about 15-20% of increase of urbanization. And these are the continents where the water challenges in urban centers are already critical, which means that they are going to face a huge problem in the time to come. Another thing which I forgot to, I lost that slide here. I said that the world population is increasing by 50% from year 2000 to 2050. 70% of our water is used in agriculture. So you can also say that, okay, 50% increase of population means 50% increase of this 70% increase. But it is not that. We all eat much more than our parents and grandparents did. Right? So it means that it is not only the today's 70% of water we are talking about. We are going to need much more water than what we used or what our grandparents used. So which means that we are heading for a crisis for sure. Crisis is going to be there, so but maybe we can reduce the impact a bit, right? So the urbanization means that we need to build new drinking water treatment plant. We need to build new wastewater treatment plant. We can't find new resources, but maybe we can have some desalination plants, but it is also so costly. And for the most of these urban centers in Asia, Africa, and Latin America, desalination is not within the affordable range. So, but you need to produce drinking water. You have to treat drinking water. You have to treat your wastewater. So, which means that you have to build exist in drinking water plants and wastewater treatment plants. For a conventional engineer, well, if you have a treatment plant which produces drinking water for 100,000 people or 1 million people, if the population is going to be 2 million within the next, let's say, next 10 years or 15 years, the conventional or the simplest method is say that, okay, we'll expand, we'll build another treatment plant. Here comes the issue. So places like, that's probably Dhaka, and this is probably, I don't know, maybe it's Brazil, maybe you might know it from Brazil. So where do you find space to expand a treatment plant? There could be space, but the municipalities, they cannot afford to purchase that because they cannot compete with the real estate developers. So in that sense, the solution is to reduce the footprint of treatment plants. Of course, we have done a lot. So if you think about the activated sludge plants, when you move from activated sludge to biofilm systems, you are reducing the footprint by 70%. And if you move from biofilm to MBBR, moving bed biological reactors, you will reduce it even further. And then you can have, the newest versions of MBBR, like CFS, you can reduce even less. And there are ways to deal with it, like if you install a micro screen in front of your, let's say, the first sedimentation primary settling tank, or before the coagulation, then you can remove maybe almost 50% of your particles. So microscreens of 1 or 2 millimeters is quite common, but now there are microscreens down to 0.5 millimeters, and I know of quite a few applications in Scandinavia where the microscreens are down to 0.1 millimeter. And there are companies who are experimenting now, microscreens down to 0.5 microns, 0.005. So the technological advancement here is that innovators has found to avoid clogging of these filter screens. So simple example is that there's this it's a Norwegian company called Salsnes Filter, which was bought by the Canadian Trojan. It's marketed under Trojan now. It's like a conveyor belt, so the water comes in. This belt is with a very small opening, pore opening, so the belt is going up. It carries all the waste to the top, and when it comes to the top, there is a water jet, so cleaning the filter material, filter bed. So when it comes down again, yeah, it's fully clean. So it's like continuous process. So these are some examples. Right? By the way, please ask questions. So let's keep it as a discussion, not as a one-way lecture. So, and I have not so much well structured this as well. I put many things to this presentation. So how much water we use per day? Any idea how much water you use per person in Canada?
250.
What?
250 liters
250
per day per person.
Yes.
Yeah.
So this is the North American version of water use. Right? If you say 250 liters in Europe, you will be shocked there. So our average is 100 to 150 liters per day per person, right? And we try to come closer to 100, but US and Canada, I think the biggest challenge is that you are using water for watering of your fields, and there is a fair percentage of wastage in the domestic uses. But if you look at the figures in Nairobi, so we are talking about maybe 50, 60 liters per day. And if you look at the wage numbers in these slums, Kibera, so we are talking about less than 10 or 15 liters per day, which we cannot comprehend, right? Let's say 250 liters, but the problem it is not with us 250 liters, so we use much more than that, right? So, has anyone heard about the virtual water footprint? If not, you should Google it and read about this. It's very interesting stuff. Introduced by a Dutch researcher about 15, 20 years ago. What he says is that a pair of jeans, to produce one pair of jeans, you need to have 8,000 liters of water. Well, you can also live with that because you don't buy a jean every month, right? But if you look at this table, this is where you're going to get the shock of your life if you haven't seen this, right? To produce 1 kilo of beef, you use 15 tons of water, starting from the grass and also the processing and everything, right? So that's why I'm saying that we have to change our traditions. Some of you are way ahead of us, like Professor Brad. No meat. But we have to change this tradition of using, the beef produced from beef and pork. So, in a way, some of us are used to have steaks and beef, and that's why some countries have already found ways to produce this artificial beef. I've seen Israelis have produced some steak, and Netanyahu, or one of the presidents before, when he mentioned this lab, he tasted this, he couldn't see and he couldn't find any difference. That's completely vegetable based. It's much better than the veggie burgers what we see here today. So this is an example. The other example is the rice. A great part of the world we eat rice, but the rice is, in a way, is a curse for the mankind because it uses maybe 1,000 times more water per kilo produce rice or maize. If you have seen rice fields, I'm sure that you see that it's most of the time the rice paddy fields are flooded with water, right? So it's a waste of water. We have to find a different ways. But there are innovations, like this Chinese professor found this long pin rice. He claims, so usually per year, 2 harvests are common, right? 1 to 2 and maybe 3. But this guy has come up with a solution that you can have up to 6 or 7 time harvest per year. So it changes the whole thing. And then there's another group of researchers it's working on, it's called perennial rice, which means that you have, after harvesting, you are not taking out the whole rice plants. You can have re-harvesting 2 or 3 times. So there are ways to do it with that, so we are working on that. So this is a figure that we have to think about, and even an apple takes 70 liters, coffee, 1 glass of white 120, coffee is 140. So these are crazy numbers. Of course we can say that beef is coming from Brazil, Argentina, so it's their problem. Or 80% of your clothes were coming from China before Trump's time, but it might go down now because of the taxes, and so it's a Chinese problem, you can say. But we have to think about the world. Because why do we work with wastewater treatment in Canadians and Norwegians? We don't have a problem with water, but we do it because we have to do it. We have to show, we have to invent solutions, we have to show it to the world, and we have to also involve in other parts of the world's challenges. biggest problem is the climate change makes drier places even drier. So even today, 70% of the world's population is affected with water scarcity at least 1 month per year. Even in Norway, in our big cities, during the summer months, there are restrictions to use water for gardening because we don't have enough water. So now we are also starting to think about the reuse of water. But this is a part of the place. All these brown places means that there's a challenge with water scarcity induced or increased due to climate change. The other part of the world is too much water. So these are figures from Copenhagen, the capital of Denmark. In 2011, the whole capital was underwater because they got 320 millimeters of rain within 4 hours, and there's no way to take this water out of the city if you get so much water in time. If you are thinking the traditional way, it's not going to happen. And they did a lot of things and they thought that okay, it's solved, and then in 2014 the same thing happened, the city was underwater, but after that they start thinking a different, completely different way. So in Scandinavia, yeah, but if you ask your parents or grandparents, they would say that no, we didn't have this flood problems in the cities, because when there's a rain comes, we had permeable surfaces, the water could go vertically down. But now we have efficiently covered our surfaces, including York University surfaces. It has either asphalt or concrete. So when the water comes, there's no way to go it down, right? So that's why we have to educate all these landscape architects. Put something else. You can still put, you can put something like these concrete blocks with a hole inside. So you can walk, you can park, you can drive, you will feel the difference, but because that there is an opening in the middle between, so when the rain hits, it will go down. And then we have some other examples, like in Stockholm, in Sweden. There are a couple of places we have built playgrounds below the road level. So when there's no rain, it's a playground. So basketball, hockey, or whatever, football ground. But when there is a big rain like this, it turns into a pond. So all the water is collected there. Instead of flooding our houses, it collects water into this pond. And after maybe 2, 3, 4 days, when the rain is away, so the water is gone down. So then you start using it for recreational purposes. So this was an introduction to the brief reminder of the challenges what we face and how we are trying to solve this in different parts of the world. And it is not a comprehensive list, but it is just showing the flash information. And then let's look at the innovations in water quality management, which was the main topic of this speech. So in this part, I will talk about the virtual sensors and validation of measurements, estimation of missing parameters when our sensors are not working, and how it is used in process analytics. So the water quality analysis in general, they are used in the laboratory. They are done in the laboratory using traditional methods. The instruments are becoming more and more advanced, but the concepts remains the same. So there are online analyzers which can analyze maybe 50 or 200 robotize the system what we are doing. So if you're going to measure phosphates, you take a sample and you add chemical A, mix it, chemical 2, mix it, chemical 3, mix it, and let it stay for some time. COD that you will also have to heat it, and after that you measure the absorbance, right? So everything's automated. So these instruments are quite handy for the laboratories which measure these parameters in the bulks. They are using this because it saves time, especially this part of the world where the labor cost is very high. So, and then there is a need for the real-time measurement. So we cannot wait 1 hour, 2 hour, or 1 day, or several days until we get the results from a laboratory to optimize our treatment plants. Because our waste, if you think about the wastewater, our wastewater quality is changing. We say that every 15 minutes our wastewater quality changes, but at least every hour it changes, right? So if you're going to get your results after a day, then the train is gone, so you cannot do anything with that. And so that's why we need to know the water quality, the inlet and especially the outlet immediately, so that we can do some actions to corrective actions. So to do that, we have to measure the water quality in real time. So to do that, there are a number of real-time sensors. There are many accurate and affordable sensors, but they require maintenance and sensors. So they will not work 24/7, 365 days. You have to maintain them. So there are, even if you maintain them, they might not work all the time. So how are you going to deal with that if you're going to involve both not only measurements but also use it in your process control, right? And there are no sensors for all parameters. So for example, phosphates, there are no real-time physical sensors. There are analyzers which gives you the results after 10 or 15 minutes, but expensive, quite expensive. And if you take the emerging contaminants, there are no such sensors or real-time systems. Biggest problem is many systems are not affordable. They are quite expensive and difficult in predicting the treatment results. This is the other thing. We cannot say what's going to happen if we add this chemical or if we have the biological process. What would be the final result? We can of course say average results what's going to happen. So this is a schematic figure for a drinking water treatment plant, conventional water treatment and a wastewater treatment. Right? Drinking water, we have a strainer, and then we have a coagulation stage, 2-meter filter, granulate with carbon to remove odor and taste and whatever, and that we have the disinfection part going on, adjusting the pH. In wastewater, there are different configurations, so it shows that we have biological pre-treatment or biological treatment to remove organics, and then we have the coagulation to remove the remaining particles and phosphates. Going out here. Before, it was enough to measure the water quality at the outlet and say, yeah, we are doing our job, it's good enough. But the times have now changed. We need to measure these parameters also in between the processes, and the inlet and in between the processes. So if we want to optimize this part independently of this part, we need to know the incoming water quality here, outlet here, so that we can optimize this process. When we talk about the removal of emerging contaminants, so what today we measure the emerging contaminants concentration at the inlet and outlet, and then we start proposing, yeah, let's add this unit process or this unit process. But I try to convince that, okay, we may need to do this, but yet if we run our processes more optimally, we can remove much more than what we are removing today. But to do that, you need to know the water quality between the systems. So if you can measure the concentrations here and there, then you can see that, okay, how we can optimize our processes or super optimize our processes, so the removal of this stuff will be much higher, and the additional process what we have to add here or here or here will be more, will be less, and less in volume and maybe also less in costs. So detection methods, if you take the high-end methods like for PFAS or pharmaceuticals, they're expensive, high time consumption, skilled technicians are needed, limited sensitivity and selectivity, and especially if you're working with emerging contaminants, and you know that we are talking about the nanograms, use of toxic chemicals sometime, and limited accessibility. So we have to find a way to go away from them. So there are examples. Has anyone come across with this sensor, this company called SCAN? In your laboratory, the spectrophotometers, they are, I guess all of them are scanning spectrophotometers, right? So you put a sample and it gives you the spectral from 220 until 800, right? When Professor Brad and me, we were at the university, we had to measure the absorbance at 450, got the result. And sometimes that spectrophotometer measured only at that absorbance, at the wavelength. Sometimes we could turn it and we can measure maybe 3 or 4. But now we're in a different world to get the whole thing right. So this company, this is an Austrian company, they are probably the first in the world who produced the sonde, which produce the scanning spectra. Right. So here's the results, right? So they start from around 200, low 200, and going up to 800. So in a sample, they will get this spectral wave absorption curve, right? And then this absorption curve is influenced by the particles in water. Right. So since you can measure particles like turbidity and particles also with the same instrument, you can subtract that, and then you can have the net absorption curve, which is shown in red here. And then you can have algorithms to convert the absorbance at, for example, here 420 into the color milligram per liter, right? The same way like COD, BOD somewhere here, nitrates and nitrates are here, and some other parameters. So you do the scanning or analysis at once within seconds, and in the screen that you will see all the parameters measured. So soon after this Austrian company scanned, then there was a German company called System Electronica started doing the same thing. What they say is that they can measure anything, but not phosphates. Apart from phosphates, they put everything else. So those are drinking water, groundwater, river water, sea water, and wastewater, paper mill, industry, everything. And the blue sign means that this sensor can give you all the measurements. So there are some versions of this instrument. So it's like a wonderful instrument. It is, but there are divided opinions or experience from the users. Some are very happy. Some say that it's not as what they say. Some countries have bought these instruments. They put, I think, 100 or 1,000 units along Ganges. 100 by 200. But so a unit cost about close to 20,000 euros. It's pretty expensive, so you cannot have it in different places in treatment plant, or especially for the smaller treatment plants, right? But the concept is interesting, and this is the concept that which my research group has used to develop so-called hybrid sensors. the explanation is like turbidity measurements is that you take sample, put to a turbidity meter, and you get the reading within 2-3 seconds, right? But if you want to measure the suspended solids, you have to put a filter, weigh the filter, filter your material, and you dry the filter, and then weigh it, subtract, and you get the suspended solids or total suspended solids after 2 hours or 3 hours time. But at the same time, now there are sensors which can measure suspended solids momentarily. So the principle is quite simple. There is a linear relationship between the turbidity and suspended solids. So they measure suspended solids. Now they measure turbidity and they show the suspended solids because there is a linear relationship, right? So you can even use Excel to develop this relationship. And then there are many suppliers of these suspended solids sensors, and the leading Western producers, they would charge maybe 100,000 Canadian dollars per sensor, but while there are now Chinese sensors in the range of 5,000 to 20,000. 10,000 Canadian dollars is the price of European or American brands, but you can get it for like 10% price from the Chinese brands. But it's not about suspended solids. Suspended solids anyone can measure, right? So we wanted to measure what is required, like COD, phosphates, and nitrogen. And here you cannot do it with Excel or simple ways. So what we are doing is that we install few of these cheap and simple sensors like the flow, pH, conductivity, and eddy turbidity. They measure continuously in a treatment plant. And then we combine those measurements with historical data, and then we have algorithms to estimate COD, phosphates, and nitrogen species. And we can do it for many more. So working perfectly fine. So here you can see the correlations of more than 96% for phosphates, and here for COD around 88%, but these figures are from 3 or 4 years back from these publications what we have. But now our prediction accuracy is over 95% for phosphates, and COD and BOD and nitrogens between 90 to 93%. So we started this with statistical methods, but now we are using machine learning and AI can make it even more accurate. So we call it as hybrid sensors because it uses both physical sensor measurements and historical data. If you take a scan system, it uses only the algorithms. So it's not a hybrid system. It just measure one absorbance data and use it in algorithms. So I believe that future virtual sensors will give us solutions to measure microbiological water quality. This is one of the biggest challenges that we have today. Still, there are no accurate methods to measure the microbiological quality in our drinking water plants within hours. The traditional methods takes 24 hours. There are simpler methods which you can get some idea between 6 to 12 hours time. But if you want to wait until all the analyses are in place, you have to keep that water without releasing it to the public. No city has that capacity. You're talking about hundreds of thousands of cubic meters, right? So what every treatment plant does is we do our best to remove all the pathogens and also doing disinfection, and we discharge it, and then we also do control measurements in the lab, but before we get the results from the lab, we will get a call from a doctor saying that, "Hey, look, now there are 15 patients with diarrhea." So doctors find it before us, we get the report. So we have to change this. Like, how do I going to do this? So I'll show you some examples, some quotes. So we have disinfection byproducts. Disinfection byproducts are, like we know about the chlorine is the most common method to disinfect. And in order to be sure, we add more chlorine. Whenever I go to a new city and if I look at the swimming pool, and if there is a chlorine smell, I feel safe to take a swim. It means that they have added some chlorine, right? But now things are changing because some hotels, they use UV or ozone, especially in Americas and Europe. So it's also. But if you're going to Asia and Africa, so it's good to feel that there is some chlorine smell in your water. But the downside is chlorine also creating disinfection byproducts, right? Even ozone it creates, right? So how do you deal with that? You need to measure it in order to eliminate it. Emerging contaminants. This is one of the major activities what Professor Brar's team and my team is working on. We are still not there to provide an affordable and fast enough method to measure CECs. So in Norway, I have to pay like 400, no, like 600 Canadian dollars per sample to measure CECs. Maybe it's also the same range, right? Yeah. And the laws are changing. Now there's a new law coming from next year. All drinking water treatment plants, no matter how size it is, they have to measure emerging contaminants at least 4 times a year. Some of the treatment plants are so small that they can afford to do that. And then water quality, how to measure the water quality in pipes and sewers, like this one. So drinking water pipes and wastewater pipes historically, we put our drinking wastewater pipe at the bottom, and then we put the rainwater pipe, and then we put the drinking water pipe. So even if wastewater pipe is leaking, the wastewater is at the bottom layer, right? And then we have rainwater. So drinking water pipes are somewhat higher in the level, so less contamination problem. But let's say that we avoid that problem and we start transporting our water from a treatment plant to our consumers who lives 10 kilometers or 50 kilometers away from the treatment plant. While it is transporting, water can get polluted. Also from intrusion from wastewater, but also something happening inside the pipes and the fluids. If you happen to see inside of water distribution pipes, better not to see it. If you see somewhere that someone is digging the drinking water pipes, don't look at it, then you get the shock. Be drinking water from these pipes. It's terrible, so it's like this. So you have all sort of possible things in the pipes. But how are we going to measure the water quality? We cannot take samples like every 10 kilometers, every day. It's not going to happen, it's so expensive. So we have to find some sensors which can do this job, maintenance free and low cost. So here is an example, another example where we can use real-time hybrid type sensors. So when it comes to the microbiology quality, and there are sensors to measure the algae concentration in lakes and rivers. They use fluorescence. So for example, in Norway we have salmon farms in offshore. So our salmon farms, they need to know that if there is an algae invasion coming a day or two before. So if if they know it, then they can slot it and they put it to the market or relocate them. Have anyone heard about the term called ferry box? Probably not. It's some people in Europe knows about these ferries are everywhere, right? I don't know about. Yeah, I'm sure with the Great Lakes there are ferries, right? Passenger lakes, right? How do you monitor the water quality in Great Lakes? Take samples, probably, right? And you take samples, you don't take it every day because of economic reasons, and this was the case also in Norway. So Norwegian water authorities has commissioned research institutes to go and analyze, provide reports. So what they do is that during the summer they have more frequent visits, maybe every week, and other times maybe once a month. But still they miss some of these algae blooms because we are not measuring it every day. It's so expensive. Then someone came with this genius idea saying that the ferries are going here and there all the time around Europe. Why don't we install an online sensor in the cheapest cabin of a ferry? That means under the car deck, right? So there's a system that it pumps water into this cabin and water, and there are some sensors which measures online pH, conductivity, and fluorescence. And on the top of the ferry, there are infrared monitors measuring the particle concentration and get it to one of the research institutions, and it converts it gives a picture of the concentration. So the beauty is that the ferry companies, they are happy to provide that because they feel that they are part of a solution. So research institutions, we don't pay for this service. We have installed it, and as a result, we get a water quality of every 300 meters along the path. And then we use, so then we get the water concentration or the water quality in up and down this path, but our seas are so big. So what you do is that we get a satellite picture of this area, and then we calibrate the satellite picture using these real-time measurements, and we get the full picture of algae concentration and other particles in the sea, which is fairly accurate. And then if you see that algae is coming from, let's say it's coming from Denmark, and it's going to reach Norwegian west coast in 48 hours, we will give signals to our salmon farms, and they know what to do. So this is algae. Algae is much bigger than the microorganisms. So there are some research papers showing that even E. coli could be measured using fluorescence. It's not an exact science, but it shows that there is a trend, right? Fluorescence intensity can be calibrated again in E. coli. So this is something that we want to follow up with. We are working on this. Now the last part is I want to show you about our measurement practices, or some interesting measurement practices of emerging contaminants, so specifically PFAS. So we want to develop a salt sensor or a hybrid sensor for PFAS measurement in wastewater. So what we did was that we measured the fluorescence in water with PFAS concentrations. There's a nice instrument. If you don't have it, you should think about this. There's only one producer in the world. It's a Japanese company called Toshiba, and they have these two instruments. The lab instrument called Ambolog, and the mobile one is Veta. It can measure the three spectra in one sample at once: UV, visible, and fluorescence. Because everything is measured in one sample, then you can also use the models to predict, use this data. So our idea was to use this, especially if we can get fluorescent data, then we thought, okay, then we can say, if we see the emission, extinction, and then we can say correlate to the concentration. But unfortunately, PFAS is not emitting anything. So you can't measure PFAS using fluorescence. What we found was NOM, natural organic matter, can be measured using this method. So it was also documented before we started our research. We could also confirm that we can correlate NOM concentrations to fluorescence. But the surprising thing what happened was that when we had our wastewater with NOM, then we could correlate PFAS with EDM. So here's the pure samples, and here's these are synthetic samples, and then where we had PFAS 1 to 3 microgram per liter. You can see that when we had increased the PFAS concentration, so the extinction figures are changing. So we did it for the wastewater, and the final result was that here you can see red ones are the measured concentration of PFAS, and the blue ones is our estimation. So fairly fine. And this was the first set of results that we generated. So we are confident that we can go further. But of course, even within my team, so some researchers say, no, this cannot be true. This is NOM. This is not PFAS. I'm saying, look, guys, be open. I could correlate PFAS concentrations with our estimates. So there should be something. So we should not just discard this idea. Right? So now one of my students are starting a PhD on this, and here you can see the correlation is nice.
So with respect to this sensor, did you also run NOM alone?
Yes,
Okay.
because prior to this experiment, we were using fluorescence to estimate NOM concentrations.
Okay.
And then we knew that, okay, we can estimate NOM with fluorescence. And then, I don't know whether someone thought about this or happened some accident, so then suddenly we saw that there is a correlation. Impossible to tell why.
So what I meant is, so with NOM, is the excitation below the NOM plus PFAS excitation in terms of?
Yes,
Okay.
yeah. In the literature, there are some hypotheses, not only hypotheses, some documentation saying that you can add something to increase the fluorescence in PFAS, but we never managed to get that one. So one example is using chitosan with PFAS, right? So they said that if you have this Chinese research group, they said that if you have chitosan, then you will get the fluorescent signal. But the problem is with chitosan we say chitosan, but chitosan can have different forms. We could not find a way to replicate it, even after talking. My Chinese colleagues talked to the Chinese guy, but still we could not replicate it. So we are still struggling.
And,
So-
you use humic acid as the
Yes.
representation of
Yeah.
NOM.
Yeah. But this was the first level of research. I think I need to do much more to make it. This is not published yet, so it's still the first level. And then a disappointing situation with the emerging contaminants measurements. So from next year, we are going to have a law saying that wastewater treatment plants, I think, is it 18? 12 components, and it's divided into 3 groups. Each treatment plant is the EU regulation. Each treatment plant must document that they remove more than 80% of 3 of the substance, or 6 of the substances. 3. This is from EU, and I think it's not going to be enforced from before 28. But Norway, we are already talking about it. Which means the older treatment plants must. But what's the problem? So these are is it 19 of our Norwegian wastewater treatment plants, and here you can see the CECs, pharmaceuticals, and the groups that which are required to monitor by the EU. The green cells show the removal percentage of respective component in that particular treatment plant. So you can see that it varies from, okay, here is almost 0, but it's got 57, 72, maybe 70, 80 or something like that. So there is a positive removal between the inlet and outlet. But all the white cells show a negative removal. How is it possible? We have more CECs in the outlet than the inlet. And I had a master student completing she had results in June, and we all puzzled, and then we started digging into this, what's happening, and then we saw that it's not a one-time happening, it is a common phenomenon. The most plausible explanation is what they say is that during the wastewater treatment, some of these components change their structure. They release into, that's why the inlet PFAS, or let's say if you take the inlet concentration of carbamazepine, maybe 10 nanograms, but during the treatment process it increases to 20, and then in the outlet we measure 20, or maybe we measure 15, but 15 is bigger than the inlet of 10. That's why it shows a negative removal. Then you can put a question about what is this EU regulation or saying that you have to remove more than 80% of your CEC components. You can't do that because the form is changing during the treatment plant. Somewhere, sometime, we don't know, no one knows it, but we know that it's happening. So you cannot talk about removal of 80%, but you can talk about absolute removal, saying that it should be less than so many nanograms per liter. So that puts a big question. So what are we measuring in our treatment plants? And then there are, not me, but the researchers, high-end researchers who are working with this analysis every day. They say that, okay, PFAS and some of these components can stick into the glass walls or plastic walls, or the sampling is a big thing, and at the end I have to conclude that I don't know what I'm measuring. And then you know that if you look at all the research papers, not papers, just take the COD removal in a treatment plant, and people are reporting that I have removed this and that and that. We know that each researcher has their own systems, so we cannot compare the treatment processes. And here we are talking about nanograms. So what can we get out of all these research papers? Yeah, it's a pretty disappointing, but we have to find a solution. And that's That's why I'm saying to my students, and you have chosen the correct specialization, because you have a job for, you will never go out of jobs, right? All my students, even before they start the master's thesis work, they have got job contracts. Last two slides. So the other thing is that, can you predict the wastewater quality at the treatment plant at the time of when the water is entering to the treatment plant, or when you are having the first treatment process? If you are talking about the coagulation plant, then it may be 1 to 3 hours of time lag, right, from the inlet to the outlet. If you take the biological plant, it could be many more hours. So if we have a method to estimate what's going to come out at the end, we can quickly adjust our process. So these are some of our preliminary results, and you can see the COD measurements. The top figure is after 30 minutes. We can predict fairly well the concentration of the process after 30 minutes. So when it's increasing, you can see that it's deviating, and these are also first level research studies. So which shows that we can actually start to predict, find a way to predict our outlet concentrations, which means that if we can do that, then we can also quickly adjust our process parameters so that we can maximize the yield. So there are many things that are coming up with AI and machine learning, so many things are coming which you could not believe before. So I'm sorry if I created more questions than answers, but this is what we have to do. Thank you very much.
Thank you so much, Professor Ratnaweera. That was really an exciting talk. Any questions from the audience?
I have
Sure.
some questions.
Yes.
Yeah. Hi.
Yes.
Thank you very much for the presentation. I mean, you have covered a lot of water-related issues. And I want to go back to the diagram that you had at the beginning where you had the water treatment plant, wastewater treatment plant. And in that diagram, you had an arrow from, wastewater treatment plant going back to the water treatment plant. One of the beginning slides. There we go. Yeah, we're getting there. Yeah, right here, right? So that big arrow going back to the water treatment, right? I know in some countries like Israel, this is, a practice that is very water scarce. This is a practice that is acceptable, and in other countries, it's widely used for, for industrial agricultural use, right? The treated water. But in North America, as long as as much as I'm aware, this is not a practice. So what do you think, are the issues around, recycling technically water from wastewater to water treatment?
Have you been to Singapore, any of you?
Yeah.
So there's a fair chance that you drunk Singaporeans treated wastewater.
Yeah, absolutely, yeah.
Right?
But I mean, what are the hurdles in North America to be also a practice, right?
There are both social and technological, right?
Yeah.
So Singapore right now, it's over 40% of their water supply is coming from wastewater.
Wastewater, yeah.
Social side it's surprising. Before, was it like 10-15 years ago when they started, they marketed it as used water. People didn't want to drink it. Why should I drink someone else's wastewater?
Yeah, exactly.
Right? And they paid some money to this big shorts consultant that just change the name to new water, and everyone drinks now. New water is not a problem. It's the same stuff. So psychological.
Exactly. Yeah.
Right. Of course, now they have a problem still to deal with, because a good part of Singaporeans are Muslims, and they still know that we can't do this now. But Singaporeans are confident that they will solve it, and their target is to increase this percentage up to 65, something like that, within the next 10 years, so that they will stop dependency from Malaysia. Reuse of water started in Namibia in 1950s. That's probably one of the first countries to start it, right? So water what we get in Singapore is purer than any water wherever we get, right? That means technologically there is no problem. But there are legislative problems and also risks attached to. So when the treated wastewater is used in agriculture, so there are a number of legislations controlling that you cannot use it for, so there are like, you are not supposed to use it for salads or things that you eat on the surface, right? Because the wastewater, even though it is fully disinfected, they should not in contact. But you can use it for potatoes and carrots or whatever, but still you have to stop using that type of water a few months before harvesting. So there are legislations coming up, right? But I think the conservative thinking of treatment plant owners, utility owners, and the societies is the biggest challenge.
Yeah.
Right? And also, many would say that, well, I have my river, I can take water from there. Why should I bother with reusing wastewater?
Yeah.
A simpler version or less disturbing use is to use treated wastewater in household flushing, something like that, right? But then the problem is in new houses in Europe, they have this double plumbing system. So some pipes for the drinking water, but for the flushing they use the locally recycled wastewater. So it's coming up, but to have a double plumbing in an existing building is so costly, almost impossible, right? So I think the social factors are going to be a big problem if in Singapore they had a problem with people with a fairly high education and knowledge and understanding. How can you present it to the people in Asia and Africa and Latin America?
I think social perception is really
yes.
Yeah.
So there should be. I don't think that none of us can do what Singapore did to provide drinking water from wastewater. It's a long shot, but we all can use it, like start with using it in agriculture. So controlled water quality using in agriculture. But of course there are also now coming up, we are finding new problems to stop this by emerging contaminants. And microplastics, nanoplastics, right? So it's never ending thing.
Yeah.
And I have seen that this was a figure from this researcher Nazarova from 2015, and she estimated that the total recycled volume is 5% in the world. It's almost nothing. Even the places where there is not enough water, they are still not considering. They would rather go for desalination.
I actually have another comment if we have the time. So something that you also mentioned about the difficulties of sampling. So Satinder and I, we have a project and our student Ben, I'm sitting there. And this is a kind of a 4 or 5 year project on microplastic detection in Lake Ontario. So the first 2 years, the government had the money and there was this cruise, Limnos, that would go, every year would go to offshore of, Lake Ontario and would collect sample for us. So it is the second year that they have refused to collect sample for us because the government, budget cuts, and every day that technically Limnos takes off, it costs government up to $30,000, right? So this idea of, commercial use of commercial boats and, it's actually quite interesting, right?
It's interesting.
It's
And practical.
And
yeah, I have some slides I can share with you later. It shows how. So I I was working at this Norwegian Institute of Water Research before I got the full-time position at the university, which was like 13, 14 years ago. And that's the time when we developed this concept, right? So what we did was that we installed this system. So you can of course put Raman and FDR in your ferry, right? It will measure online everything. Right? So what we did was that well, in the researchers they can see how it goes up and down, right? Online, right? And we can also program. We programmed it such a level that if one of the parameters are going above threshold, automatically takes a sample of that water, and ship captain, when it goes to the next port, they just post that bottle to us, and we analyze that.
Very European of them, I would say, right? So
And then so this one is now from the Norwegian side, there's Norwegian cruise
probably if we
line.
do that in North America, a union is going to kick in and say,
Yeah.
right, so.
I mean, you mean that? Well, this is a problem with all the plant operators as well. So when we installed online pH meters and they were protesting, no, this is not going to work, this is not going to work. Why?
I know.
It works, but that will reveal that they have not calibrated it every Friday. So they don't want to miss their freedom. So this is the underlying the way of thinking. So yeah, I mean we should really consider installing these things. And what I was starting with saying is that we have a Oslo to Kiel in Germany ferry line, 16 hours, and this ferry, it's a nice ferry, like 15 floors, like a floating hotel, right? So there's a screen, big screen showing the water quality of the sea where you're passing. So the people see it, and the ship ferry line is also happy that okay, this is what we are doing for the environment.
Green ferries.
Green ferry.
All right, thank you for that. Thank you, I really appreciate it.
Thank you so much, Professor Ratnaweera. Anyway, we can continue